Welcome to Calculus 1. Let's start in the beginning, which is actually in the appendix. Appendix A1 is entitled The Real Numbers in the Real Number Line. And what we'll do in this appendix is discuss the real numbers and some other collections of numbers. We'll represent the real numbers geometrically on the real number line. And we'll consider some sets of real numbers, intervals in particular. Inequalities will be expressed as having solutions which are expressed in terms of intervals. Absolute values, inequalities involving absolute values, the interaction of all of this. So it should be familiar to you, but let's do a little refresher, and there's some fairly dull points in this when we go through and actually establish the rules by which we play in terms of how the real numbers behave. Now we're going to deal largely informally with the real numbers in this appendix. Appendix A6, Theory of the Real Numbers, is still pretty much informal as well, but it lays out a little more precisely what the real numbers are. The real numbers are a complete ordered field. Okay, field, we'll talk about the field properties. That's the algebra of how the real numbers interact under multiplication and addition. Ordered is the greater than, less than that you're familiar with. And completeness. Completeness is a bit of a long story. I strongly encourage you to watch the video for Appendix A6. It's a little over a half hour long and goes through and tries to inspire what completeness is in terms of a story of an airplane taking off. These topics are covered more axiomatically and more rigorously in a senior level class, so the details of this are not quite appropriate for Calculus 1, but without an understanding of what the real numbers are at some level, you don't understand calculus. So this is a necessary thing to go through. You don't understand all the little nuances, you'll be okay. Plenty of people are doing calculus without understanding all of the little nuances, but it's worth a try at least. This stuff is important and what makes the calculus work. But I leave it to Analysis 1, and there's a link to some notes on that to more formally define what the real numbers are. Thomas's Calculus, our calculus book, states that the real numbers are the numbers that can be expressed as decimals. And they go on something about this. Yeah, that's well, I guess that'll have to do. We express the real numbers as points on the real number line. All right, so here's where they're informally getting to the idea that we're dealing with a continuum. And this representation of the real numbers as a line is sometimes called a geometric representation. And in our travels, we'll use this font highlighted here, this double backbone R. This is the font used to represent the real numbers. So for us, it's all about real numbers, no complex numbers, no square roots and negatives as far as we're concerned. You knock yourself out on that stuff someplace else. We've got courses on complex variables at the senior level also to take care of that, where you do calculus with complex numbers. But we got enough on our plate with real numbers as it is now. The algebraic properties, or the field properties more precisely, of the real numbers deal with how the numbers interact under the operations of addition and multiplication. Now, the book also talks about the operations of subtraction and division. Really, there is no such thing as subtraction. There is addition by additive inverses. There's no such thing as division either. There's multiplication by multiplicative inverses. So there's really only two operations. There's addition and multiplication. So those are the two operations that you have with the real numbers. You won't divide by 7. Strictly speaking, you don't do that. You multiply by the multiplicative inverse of 7. So same thing's accomplished. But quite technically, there's really only two operations you do with real numbers. We got a little problem with one of those. The additive identity is denoted with this symbol here that you're used to, 0. And one little thing that we don't have is the additive identity 0 does not have a multiplicative inverse. In other words, you don't divide by 0. I can't make a big enough deal out of this, because in calculus, we're going to do a bunch of stuff where it looks like we're dividing by 0, or we're trying to divide by 0. Well, we're not, because you can't divide by 0. If you could, calculus would be a whole different story. But there is no division by 0. You can't take square roots of negatives. And you can't take square roots of negatives because I won't let you, because we're sticking with real numbers, because we got enough on our plate in terms of real numbers. But there's a course out there where people take square roots of negatives. My training is in complex analysis, so I got no problem with that. But there's not some class out there where you're dividing by 0. It's not like you learn enough math and finally they let you in on a secret of division by 0. That's not a thing. Square roots of negatives is a thing. We're just not doing it because we got enough of stuff to worry about. Nobody's dividing by 0. There's not an advanced math class where you learn how to divide by 0. That's a totally different problem. So no division by 0. To make it more tangible to you, if I ever see you write something involving division by 0 on a test, for example, I'll be taking points away from you. So don't give me the pleasure. Don't divide by 0. That's not a math thing. So in a nutshell, that's how we're taking care of the algebraic properties, the field properties, they're called in an upper level algebra class, you know, distribution of multiplications and additions and all that kind of thing. The existence of an additive identity and the existence of a multiplicative identity denoted with a 1. So we won't get into that in any more depth than that. Appendix A6 lists out the algebraic properties, the field properties precisely, so let's not bother here. The order properties, so these are properties of the idea of greater than and less than. So if we take any two different real numbers, A and B, we write A is less than B, or B is greater than A, that's how these are read, when A is to the left of B on the real number line, or equivalently when B is to the right of A on the real number line. So we're introducing this greater than, less than in terms of locations of numbers on the real number line. There's other ways to approach orderings as well. Some properties are, for A, B, and C, real numbers, if A is less than B, then A plus C is less than B plus C. Add C to both sides of an inequality, it doesn't change the inequality. The inequality stays the same. If A is less than B, then A minus C is less than B minus C. Subtract C from both sides, and that doesn't change the inequality. Yeah, this is where I might take an opportunity to complain a little bit. You know, they took care of this in their first statement, but there they go, dealing with subtraction as if it were something different from addition. I don't argue with the validity of it. I argue with the fact that there's no such thing as subtraction. You're adding negative C in this, and it's covered by the first property, it turns out. If A is less than B and C is greater than 0, hey, saying C is greater than 0 is just another way of saying C is positive. Then A times C is less than B times C. Multiply both sides of an inequality by a positive number, and the inequality is preserved. Property 4, if A is less than B and C is less than 0, well, saying C is less than 0 is equivalent to saying C is negative. And we get B times C is less than A times C. When you multiply both sides of an inequality by a negative, that inequality is reversed. Notice we've got the A on the left and the B on the right. Initially, over here, we've got the B on the left and the A on the right. So they've swapped sides. The inequality's been reversed when you multiply both sides by a negative. Nothing new to you. If A is positive, then 1 over A is positive. That's what property 5 says, written in terms of inequalities. Property 6 says if A and B are both positive or both negative, if A and B have the same sign, if A is less than B, then 1 over B is less than 1 over A. Now, they didn't divide by 0 here, did they? A and B are either both positive or both negative. Is 0 positive or negative? No, it's too busy being 0. 0 is neither positive nor negative. It's 0. So there's no concerns about division by 0 here. Got my eyes open for that because that's something we cannot do now or ever. So this says taking reciprocals reverses inequalities when I've got two numbers of the same sign. So there was that caveat, that condition. Okay, the completeness property, this is really explained in Appendix A6. It deals with making the real numbers a continuum. The real numbers don't have any holes or any gaps in them. The real number line is a continuum, a continuous line, whatever that means. It means what the completeness property says it means, actually. And it's quite an involved idea and a surprisingly new idea. This idea of completeness is only is around 150 years old. This is not that old an idea, stated in terms of an axiom for the real numbers. But the fact that we have a continuum, we have this completeness property satisfied, is totally essential to a bunch of the calculus stuff. The calculus stuff we will do dates from around the year 1700, give or take a couple of decades, depending on whether you ask Newton or Leibniz, the original two calculus folks. But calculus was dealt with initially in a very informal way. And it wasn't formalized for, well, until the mid-1800s or somewhat later than that. So it took over 150 years for these initial calculus ideas to be formalized in terms of this completeness property stuff. We see Appendix A6, you'll love it. It is kept fairly informal and yet illustrates this idea of what a continuum is. So we'll leave it at that in terms of what a continuum is, but I strongly encourage you to watch the video for Appendix A6. Set theory notation, we need a little bit of that. Our sets will usually be sets of numbers. So we'll often use set notation and set theoretic terminology. A set is a collection of objects. For us, it's usually real numbers. These objects are called the elements of this set. For set S, we write these symbols here, and this is read A is an element of S to indicate that A is an element of S. We'll write these symbols here to indicate that A is not an element of S. For two sets, S and T, the union of those two sets, indicated with the union symbol, it's kind of like a U, is the set of all elements that are either in set A or in set T. Goes without saying, or both. So S union T is all elements in set S or in set T. For sets S and T, the intersection of these sets, denoted like this with the intersection symbol, it's the union symbol turned upside down, is a set consisting of all elements that are in both set S and set T. We could go into Venn diagrams, do more detail on that. I trust you have a background in this. Our sets will usually be intervals of real numbers, is how we'll use these. And we'll talk about behaviors of functions on unions of intervals, usually, will be our main use of set theory. The empty set is a set with no elements, denoted with the empty set symbol here. Set S is a subset of set T, is denoted. S is a subset of set T if every element of S is also an element of T. So this is read S is a subset of set T. You might also read it as T is a superset of set S. The subset terminology is more common, but superset is a term you might hear out there in your travels as well. To present a set, we might simply list its elements. Here's set A, consisting of the real numbers 1, 2, 3, 4, and 5. We might also describe sets, well, subsets of a given set, usually sets of integers, sets of real numbers, by putting a condition on the elements of the set. So what we have here is a wee bit out of order. I'm going to refer to the integers. The integers, this is a set consisting of 0, 1 and -1, 2 and -2, 3 and -3, 4 and -4, and so forth. So that's the integers. And what we're doing here is saying set A consists of all x, an element of the integers, such that, this is a conditional, 0 is less than x is less than 6. In other words, x is an integer between 0 and 6, excluding 0 and excluding 6, because we got strict inequalities here. That's just another way of saying set A is a set consisting of 1, 2, 3, 4, and 5. But this idea of putting a condition with a little bar vertical bar is a common way to describe sets as well. Okay, some common sets of real numbers are the following. The natural numbers, denoted with this symbol here, an N for natural numbers, indicates the numbers 1, 2, 3, 4, 5, 6, blah, blah, blah. Zero is not included in our book for the natural numbers. There are books out there that include zero as a natural number. There ain't any books out there that include the negatives as natural numbers, but sometimes you may see zero included as a natural number. So keep an eye on that. It's surprising we don't have universal agreement on what the natural numbers are, but you take different math classes, this definition might change ever so subtly. I prefer this definition actually. The integers we talked about a second ago, denoted with a Z. It's because this symbol was introduced in Germany, and Zahlen is the German word for number. So that's the reason there's a Z, just to indicate the integers. But it's it includes all the natural numbers, it includes the negatives of the natural numbers, and it includes zero. So integers will commonly refer to the integers in some of the things we do. Mostly we'll deal with intervals of real numbers. So that'll include a lot more stuff than just integers and natural numbers. The rational numbers, Q for quotient, is a set of numbers of m over n such that m and n are integers and n is not zero, because you can't divide by zero. You ever do any division, you got to get in there implicitly or explicitly a statement that you ain't dividing by zero. So the rational numbers are ratios. That's why they're called rational numbers. They're ratios of integers where you don't have zero in the denominator. The symbol is Q because they're also called quotients. The irrational numbers are all the real numbers that ain't rational. So it's the set of real numbers which are not rational. As a set, we could denote it as x, a real number such that x is not a rational number. Your examples of irrational numbers are square root of 2, pi, actually square root of 3, square root of 4, no, square root of 4 is 2. Square roots of natural numbers that aren't perfect squares. Turns out those are examples of irrational numbers. Pi is an irrational number. E, the base of the natural log and natural exponential, is an irrational number. This is a touch peripheral. I don't think this is mentioned in our book, but here's a funny story about infinity and infinite sets. So a funny story is that these sets we just mentioned, the rationals, the natural numbers, the integers, the rationals, and the irrationals, these are all infinite sets. But it's a funny thing, they're not all the same size. The natural numbers, the integers, and the rationals, these sets are all the same size. They're countably infinite. The real numbers, the irrational numbers, these are examples of sets that are infinite and uncountable. So we've got a collection of sets here. They're all infinite, but some of them are bigger than the others. The surprise is the countable sets are not the same size as the uncountable sets. What the real implication is some infinite sets are bigger than others. So there's levels of infinity out there. The lowest level of infinity is the cardinality of the natural numbers or the integers or the rationals. It's all the same. And these are a fundamentally bigger set. Enough of that for Calculus 1. This is discussed usually in a senior level analysis class, possibly a set theory class. ETSU doesn't have a set theory class. And it's actually covered in the senior level analysis class, which I've taught many times over the years. There's a link to a discussion of some of this stuff and what it means to say two sets are the same size or the same cardinality. These are ideas that date from 120 years ago or so. These date from around 1900, give or take a little. And they're due to a chap named George Cantor. But there's some wild stuff out there waiting for you in your mathematical career if you'll pursue it to this level, and you're good to go on that kind of information. Once you've had an introduction to proof proving class, you could take these classes as a junior, for example. Subsets of real numbers are intervals if it contains at least two numbers and it contains all real numbers lying between any two elements in that interval. So that's what we're taking as the definition of interval. So a single point does not determine an interval, has to have at least two different numbers in it. And for any two numbers in it, everything in between those two numbers is also in it. That's what an interval is by our definition. We could describe this in terms of the ordering, the less than stuff a little more symbolically, but this will do. We often describe intervals using inequalities or interval notation. Interval notation is going to play a big role in Calculus 1. This table A1 I've scanned from the book. Let's magnify a little bit, maybe a lot bit, and gives the notation, the set, theoretic description, and a picture along the real number line of some various types of intervals. Parentheses A, comma B, parentheses means all real numbers X that are strictly greater than A and strictly less than B. So this doesn't include A and B. A and B are endpoints of this interval, but they're not in the interval. That's what the parentheses mean. Along the real number line, we draw something like this. So we put a little open circle at A, a little open circle at B, and then shade in everything in between. This is called an open interval. For some reasons, it'll be explained in more detail later. Closed interval, square brackets, A comma B square bracket. That's all real numbers X that are greater than or equal to A and less than or equal to B. So this time it includes the A and the B. So what we draw on the real number line is we'll take point A, shade it in, take point B, shade it in, and everything in between. A and B are the endpoints of this interval, and this time A and B are actually in the interval. They're called endpoints of the interval, whether they're in the interval or not. It's the symbol written at the ends of these intervals. AB, here we got a square bracket on A and a round bracket on B. Okay, that means include A and exclude B. Here it is written in terms of an inequality. Here it is drawn along the real number line. Include A, little shaded in dot there, little open circle over here at B, and everything in between. So this includes A, does not include B. The endpoints are A and B. Similar type thing here, except here we've included B and excluded A. Here's the picture. The open circle and the shaded in circle just swapped ends on this one. All right, how about this? Interval from A to infinity. What this means, this is our first encounter with the infinity symbol. It means all real numbers X that are greater than A, strictly greater than A. You want greater than or equal to, we'll do it a slightly different way. Along the real number line, we'd start at A, we'd shade everything to the right of A. The book draws a little light blue arrow to indicate that this goes on forever, as it were. And a little open circle at A because of the parentheses here and the strict inequality here. What's up with the endpoints of this interval? A is the only endpoint of this interval. Infinity is not a number. There is no right-hand endpoint. This one only has a left-hand endpoint. It's unbounded on the right. It starts here and it never ends. There's not a right-hand endpoint for this interval. It only has one endpoint, A. Down here, only has one endpoint, A. This time it's included, so this time we'll shade it in. But otherwise, the story's the same as before. And we have the little blue arrow indicating unbounded to the right. We could have unbounded to the left. It's denoted symbolically like this. The interval from negative infinity to B. That'd be all X, real number, such that X is strictly less than B. Okay, we go to B, open circle there, and shade everything to the left of that end. The book indicates it with this little shaded circle. We can include the B, shade it in, use square brackets over there. That only leaves one other kind of interval, the whole real line, negative infinity to infinity. Now these last ones I've read this as the interval from A to infinity. There is no to infinity. There's not an infinity there. I'm a little embarrassed to use the verbiage to infinity because there isn't a to infinity. Now that's how everybody pronounces these symbols, the interval, the open interval from A to infinity. But Buzz Lightyear was wrong. There is no to infinity and there is no beyond. There is no to infinity. We're using this symbol just as shorthand for this set, or if you like, this picture over here. So the infinity symbol, before we start this calculus stuff, is merely representing kinds of intervals. These four intervals here only have one endpoint. This one has a left-hand endpoint, left-hand endpoint. This one has a right-hand endpoint, right-hand endpoint. This one doesn't have a right-hand endpoint, these two. These two don't have left-hand endpoints. This one doesn't have any endpoints at all. This is a whole real number line. We'll shade it with little blue arrows at both ends. So there's the interval notation. This stuff we're doing in this appendix, probably the most that we'll use is this idea in table A1. This interval notation will play a huge role in lots of what we do. We could more formally define intervals as open and closed as follows. An interval is closed if it contains its endpoint. And I parenthetically put the S because it might only have one endpoint. Dude, it might not have any endpoints if it's this particular interval. But an interval is closed if it contains its endpoint or endpoints. An interval is open if it doesn't contain its endpoint or endpoints. I leave it to you to think through the logic behind the claim that the whole real number line is both open and closed. Yeah, I think I'll leave that there. And this is not a universal definition of open and closed either. It's consistent with claiming that the real number line is both open and closed. I think I'll leave it at that. It's the only set that's both open and closed, other than maybe the empty set, but the empty set's not an interval. Intervals had to contain at least two different points. Intervals are half open if they are of this form. So here we've got something that's half open. Worded it if it has two endpoints and it contains exactly one of them. An interval with two endpoints is a finite interval. So let's see, finite, 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 not finite, not. So these are infinite intervals and these are finite intervals. This one has only one endpoint. Got a left-hand endpoint. This one has only one endpoint. It's got a left-hand endpoint. This has only one endpoint, right-hand endpoint, right-hand endpoint, no endpoints at all. So these guys here with the infinity symbols, these are infinite intervals. The endpoints of an interval are called boundary points. We'll use that terminology a little bit. The non-boundary points of an interval are called interior points, and we'll use that terminology a little bit more. So this idea of endpoints or boundary points and interior points of an interval will play a big role when we do some things related to continuity, related to differentiability, and these are some of the ideas we'll deal with in Calculus 1. So this terminology matters. We often express solutions to inequalities in terms of intervals. So let's do one of the exercises. We're given an inequality, and they want us to show the solution set on the real number line. Let's maybe write it as an inequality as well. So let's go to the supplements for Appendix A1, where we'll work that problem. It's basically a solve for X type question, but it's got an inequality in it. Okay. Well, we know some properties of inequalities. They were spelled out in number, and I've quoted them by number here, but we'll just talk our way through it. Let's take this given inequality and multiply both sides by 15. Because I got a 5 in the denominator here and a 3 in the denominator there. We multiply both sides by 15, I get rid of the fractions. Oh, and that doesn't change the inequality. Multiply both sides of an inequality by a positive number, the inequality is preserved. So it points in the same direction. That was Inequality Property 3 when we had our list. So multiply both sides by 15. Simplify. Let's see, 15 divided by 5 is 3. 3 times 4 is 12. We'll have a 12 out front there. 15 divided by 3 is 5, so we'll have a 5 out front there. Okay, so that simplifies to this. We can distribute. That becomes 12x minus 24. 12x minus 24. 5x minus 5 times 6 is 30. 5x minus 30. Okay, so the original inequality is equivalent to this one. Remember, we're basically solving for x. So I'm trying to get x by itself. All right. Let's do this very first one in agonizing detail. We'll always do them in this level of detail. Let's add 24 to both sides. Why would you want to do that? I'm trying to get rid of that negative 24. So we'll add 24 to both sides. By the way, that doesn't change the inequality. Inequality property number 1 tells you that. So add 24 to both sides. Let's simplify. Negative 24 plus 24 is 0, so we can drop that, and we're just left with 12x on the left-hand side. On the right-hand side, we got 5x minus 30 plus 24. It's 5x minus 6. So we got 12x is less than 5x minus 6. All right. We're trying to get x by itself. Let's get all the x's on the left-hand side and the numbers on the right-hand side. It's a strategy that's being applied. So let's subtract 5x from both sides. That doesn't change the inequality. You can subtract the same thing from both sides. Inequality property 2, I complained about it when we stated it. Subtract 5x from both sides, and that produces 12x minus 5x is less than 5x minus 6 minus 5x. Of course, we get the cancellation there. You're left with a negative 6 on the right-hand side. 12x minus 5x is 7x. So we get 7x is less than negative 6. Let's multiply both sides by 1/7, or if you like, divide both sides by 7. Funny thing, the book didn't state any rules about inequalities and division. They didn't have to in their defense. Yeah, they didn't have to for subtraction either. Whatever. I'll follow their rules and apply inequality property number 3. It says I'm going to multiply both sides by 1/7. That gets the x by itself, and we end up with x is less than negative 6 over 7. So there's the x values that satisfy this inequality. Okay, there's where we left off in the previous slide. As a set, we could write that as a set of all x a real number such that x is less than negative 6 over 7. As an interval, we could write it as the interval from negative infinity to negative 6 over 7, not including, little parentheses, not a square bracket, not including negative 6/7. It was a strict inequality here. Or on the real number line, we can draw a picture like this. So we go to negative 6/7, put a little open circle there because that's not included, and shade in everything to the left. Shaded it in blue the way the book does. So there's that inequality solved for x, producing this, expressed as a set, expressed as an interval, and expressed as a drawing. So we did what they said they asked for and more. Back to the notes. Absolute value. The absolute value function of x, a real number, is defined as follows. The absolute value of x equals x itself if x is greater than or equal to 0. And the absolute value of x equals negative x if x is less than 0. Negative x. Is negative x positive or negative? Well, it depends on x. Here, x is negative. So negative x is a negative, the minus sign out front, times a negative. The x itself is negative. That's what they say right here. So negative x is itself positive when x is negative. It's a negative times a negative, which is positive. So no matter how you slice it, absolute value of x is never negative. It's a non-negative number. It can be 0. If I plug x equals 0 in, then we get 0 out. Otherwise, it's positive. Remember, 0 is neither positive nor negative. It's too busy being 0. But it's not positive and it's not negative. So when you take the absolute value, you get out a non-negative result. So you get out positive when you put something other than 0 in, and you get 0 out when you put 0 into the absolute value function. we're going to use absolute value in calculus early on in chapter 2. We'll use the absolute value function to measure the distance between 2 points on the real number line. If A and B are real numbers, the distance between A and B is the absolute value of A minus B, or if you like, the absolute value of B minus A. I don't have to be careful with the order because I got absolute values around it. The absolute value function forms a metric on the real number line. It tells you how to measure distance. And the first topic we're going to do calculus-wise is on limits. And limits are about things getting close to each other. And its absolute value we'll use to measure distance and describe that closeness. So that's why absolute value comes up in this preliminary material. Yeah, chapter 2, limits, distance. Okay, we could also define the absolute value of x as the square root of x squared. Remember, for any non-negative real number x, the square root of x is non-negative. That's the meaning of the symbols. You take the square root of something, you get a non-negative result. You live under the constraint that you can only take square roots of non-negative things. We can't take square roots of negatives. That's somebody else's problem. But when you take a square root of a non-negative real number, you get a non-negative number out. Square roots are never negative. That square root symbol means take the positive square root or non-negative. 0 gets in the way with this conversation, but square roots are never negative. When you write the square root of 9, you mean 3. I'm hesitant to write something down that's wrong, but put it in boldface. We don't have the square root of 9 equals plus or minus 3. This is false. The square root of 9 does not equal plus or minus 3. The square root of 9 equals 3. Ask your calculator. Enter 9, hit the square root button. It'll tell you 3, not plus or minus 3. You may be interested in plus or minus 3, but the meaning of the symbol square root is that you never get negatives out of square roots. If you want the plus or minus 3 when you're taking the square root of something, you got to put the plus or minus in front of the square root symbol, because that square root thing is only going to give you the positive one. You want the negative one, you got to ask for it. So you have to put the plus or minus in front of the square root if you want both the positive square root and the negative square root. That's why the quadratic equation reads negative b plus or minus the square root of some stuff divided by 2a. The plus or minus has to be in the quadratic equation because you're looking for 2 things. Square root function won't give you 2 things. It'll only give you 1. This is surprisingly important. It's subtle, but important. So whenever you see the square root of something, you know the sign of it. It's positive or 0, but it ain't ever negative. We're going to analyze functions and be interested in whether they're positives or negative. If they're square roots, they ain't negative. So this will play a role when we deal with things like that. It'll be when we apply first derivative test to a function and we're graphing functions in chapter 4. Some properties of absolute values. The absolute value of negative a and the absolute value of a itself are the same. The absolute value of a product, AB, is the same as the absolute value of a times the absolute value of b. The absolute value of a quotient, a divided by b, is the same as the absolute value of a divided by the absolute value of b. Yeah, I can't have b be 0 because we're doing division by b. And this last one, this one's more complicated. The absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. This last one is called a triangle inequality. You take many more math classes and you're going to hear about the triangle inequality again. You'll hear about it in linear algebra, for example, the sophomore level class. We're going to go through and do one of the exercises in the book that deals with establishing the triangle inequality. We'll use this in Calculus 1, not a whole lot, but it's going to come up now and then. So let's look now at the supplemental documents that goes through and proves the triangle inequality. Exercise 24 from this appendix. Okay, they actually go through and do the computations, and they just ask us to justify their steps. So give the reason justifying each of the numbered steps in the following proof of the triangle inequality. Okay, here's a triangle inequality at the bottom. So we're trying to get there. They're starting with the absolute value of a plus b squared. Yeah, they're going to take a square root at some point, and that's how they'll get the absolute value of a plus b. But first step, absolute value of a plus b squared equals a plus b itself without the absolute values squared. Step one, why is that true? What do you know about absolute value? I know it's non-negative, and I know things when they're squared are non-negative as well. We know when we square a real number, we get out a result that's non-negative. No complex numbers for us. So you square a real number, you get out something that's non-negative. Then a plus b squared is the same as the absolute value of a plus b squared, because the absolute value of something is the same as the thing if the thing is positive. I can, if I know I'm dealing with, should say non-negative, if I know I'm dealing with non-negative quantities, I can slap those absolute values on there or ignore them if I know I'm dealing with a non-negative quantity. If I'm dealing with a negative quantity, I can maybe get rid of the absolute values, but it's a little more complicated. But here, this is non-negative, so it equals its absolute value. It's the very definition of absolute value. Now, the absolute value of a product is a product of the absolute values. We just stated that, as in this previous thing. I'll go through and we'll document all the details. I mean, that's what they wanted us to do, was justify the steps. But it was property 2, which stated that the absolute value of a product is the product of the absolute values, that allows us to establish property 1 as follows. We take a plus b squared absolute value of, that is the absolute value of a plus b times a plus b, because that's what squaring means. And now we got a product. Well, the absolute value of the product is the product of the absolute values. That's what property 2 states. Now we've got the absolute value of a plus b times itself. So we can write that as the absolute value of a plus b, quantity squared. So that establishes step 1 as follows. We're trying to show absolute value of a plus b squared equals a plus b squared. Well, we know a plus b squared equals this thing here, and this thing here equals the absolute value of a plus b, quantity squared. So paste those together, and we get that the outermosts are equal. The a plus b squared equals this thing, the absolute value of a plus b squared, and that's the first step. So that justifies step 1. That's how we get from here to here using the properties of absolute value. Okay, I'll recopy the equation on the next slide. They didn't ask us to justify this step. They multiplied out. They FOILed it. They squared this out to produce that next line. They didn't want justification from that. We'll have to see how they got from here to here. Any insight? They've replaced the a with the absolute value of a and the b with the absolute value of b, and they also picked up an inequality at that stage. So next slide. How'd they do that? You should probably suspect and even believe that a is less than or equal to the absolute value of a. But why is that? Well, let's go through and establish it. By the definition of absolute value, if x is greater than or equal to 0, then the absolute value of x equals x itself. The absolute value doesn't do anything when you put non-negative things in. If you put something negative in, if x is less than 0, that is, if x is negative, in which case I could write this as negative x is greater than 0. Inequality property 4, the reversal of the inequality, multiplying both sides by -1 is what we've done there. Then we get that the absolute value of x, when x is negative, is negative x. Very definition of absolute value. Look back at the definition. When x was negative, the absolute value of x was negative x. You sure this is positive? Yeah, it's a product of two negatives. X is negative, we just said that, and we've multiplied it by -1. So negative times a negative is in fact positive. So yeah, negative x is positive because of the sign of x itself. Don't read into this that that negative sign out front implies that this quantity is negative. It depends on what x is. If x is positive, then negative x is negative. If x is negative, then negative x is positive. And that's what we have in this case. So we get negative x is greater than 0, as we had up here. You know 0 is greater than x. That's what we started with, just writing this with the 0 on the left and the x on the right and reversing the arrow. So what we've got in both cases is x is less than or equal to the absolute value of x. When x is positive, they're equal, and when x is negative, absolute value is greater than x. Yeah, absolute value is greater than x. So we do get this x less than or equal to situation, comparing x to the absolute value of x. So that wouldn't have been a bad property of absolute values to mention back in their list, but they didn't. So we'll take x to be a times b. Then we have a times b is less than or equal to the absolute value of a times b. Just replace x with the ab stuff. Hey, the absolute value of AB, that's a product. And the absolute value of the product is a product of the absolute values. We did that on the previous slide. It was absolute value property 2. So we can string these together as AB is less than or equal to the absolute value of AB, which equals the absolute value of A times the absolute value of B, as we just established here. So AB is less than or equal to absolute value of A times absolute value of B. Excellent. We could multiply both sides by 2, and that wouldn't change the inequality. For the record, that's inequality property number 3. And now maybe add A squared plus B squared to both sides of this, and that doesn't change the inequality. It produces this, which it's not in the same order, but that is what we get going from this line to this line with an inequality in between. So this is exactly what they wanted us to justify in step 2. So this argument justifies step 2. Next, they're replacing A squared with the absolute value of A squared, and they're doing the same thing for B. So we need to justify that. Shouldn't be too hard. And then they're doing some algebra, and then there's a final step. Okay, so we need to justify step 3 next. Okay, well, x squared is greater than or equal to 0, property of real numbers. So x squared and the absolute value of x squared are the same. Definition of absolute value. Also, the absolute value of x squared, that is the absolute value of x times x, is the absolute value of x times the absolute value of x. Tedious stuff, I know. This is where we start. Absolute value property number 2, the absolute value of the product is equal to the product of the absolute values. So we can say that x squared equals the absolute value of x squared, which in turn equals the absolute value of x times itself. That is the absolute value of x squared. So we can draw that conclusion. Now, if you take x equal to a, this held for all x real numbers. We take x equals to a, we get a squared equals the absolute value of a squared. Take x equal to b, you get the same kind of thing for b squared. And that's how you can replace this a squared with this absolute value of a squared. And similarly for the b's. So that justifies step 3. How about this next one here? Where'd this come from? Oh, they just factored this. If you'll take absolute value of A plus absolute value of B, square it, FOIL it, it'll produce this. So that's why that equality holds. The same reason that one held there. They've just done distribution and properties of multiplications of real numbers. FOIL is what they've done. Okay, so that just leaves step 4. Notice what we've established. This thing squared is less than or equal to this thing. Maybe that thing squared. How about thing 1 squared and thing 2 squared? We need to get rid of the squares. We'll take square root. So let's do that. So what we have established before we look at step 4 is absolute value of A plus B squared is less than or equal to absolute value of A plus absolute value of B squared. This is less than or equal to that. So we'll take square roots of both sides. All right, now, square root function, where it's defined, is an increasing function. You should be familiar with the graph of the square root function. It's half of a parabola. It's an increasing function. It preserves inequalities then, at least inequalities involving non-negative numbers, and we got stuff squared, so we've got non-negative numbers. So because the square root function is an increasing function, we can say the square root of the left-hand side is less than or equal to the square root of the right-hand side. Now, the square root of x squared equals the absolute value of x. We made that observation in the note before we started this. So here we've got a square root of something squared. Here we've got the square root of something squared. Okay, well that's the same as the absolute value of the something. The something is the stuff in the parentheses on both sides. So we get the absolute value of the absolute value of a plus b. And on the right-hand side, we get the absolute value of the absolute value of a plus the absolute value of b. So you get these absolute values picked up. If we can drop them, we're in business. Of course, we can drop them. Nothing in sight is negative. We've got absolute value of absolute value, so that second one's not needed. The absolute value of a plus b is greater than or equal to 0, definition of absolute value. So we don't really need the absolute value. The second absolute value on the left-hand side, also the absolute value of a plus the absolute value of b, that's greater than or equal to 0. Add two non-negatives together, get something that's non-negative. So we can drop the absolute values on the right-hand side as well. So we're taking absolute values of quantities known to be non-negative. You can drop the absolute values there. That's the only time you can drop the absolute values is when you know how properly to get rid of them. You cannot ignore absolute values. You can maybe get rid of them if you justify the steps. You can get rid of them when we're dealing with non-negative stuff like we are here. But if you're dealing with stuff that could be positive or negative, you might be stuck with those absolute values. At least you have to break some things into cases. But that establishes the taking of the square root, and that establishes step 4. So, triangle inequality for real numbers. Back to the notes. Like I said, you're going to be seeing some more triangle inequalities in your travels. We can relate intervals and absolute values as follows, and we'll be doing some of this in some of the manipulations when we're graphing. This will come up. Let a be a positive real number. The absolute value of x equals a if and only if x equals plus or minus a. A is a positive real number. Yeah, I was a little worried we might be getting absolute values that are negatives. A is a positive real number. So yeah, the only time we'll get the absolute value equal to a is either when we have a itself or negative a, and the negative would be absorbed by the absolute value. Absolute value of x is less than a if and only if x is less than a and greater than negative a. It might be worth your while to convince yourself of that fact. This is how we'd take an inequality involving absolute values and write it as an inequality not involving absolute values. That'll be a thing we'll be doing along the way. Absolute value of x is greater than a if and only if. We actually get two conditions here. If x is greater than a, then this will occur. If x is less than negative a, you'll also get this condition to occur. Might be worth your while talking yourself into that as well. But these are simple properties in terms of distance. Think of it as measure absolute value of x is a distance from 0 being greater than a and what that implies. But both of these, convince yourself of those because we will use those along the way. And properties 8 and 9, they've actually numbered these things sequentially from 1 upstairs. These are the same as 6 and 7, except they put or equals to on the inequalities, and they've got the same type of structure over here on the right-hand side. So let's do 3 problems, and that'll take care of this appendix. As follows. Okay, they give us an inequality involving absolute values and ask us to express a solution set as an interval or a union of intervals and show the solution set on the real line. Okay. All right, so we need to get rid of the absolute value and then solve for y. Absolute value of a quantity is less than 4 means that quantity is less than 4 and greater than -4. It's sandwiched between -4 and 4. Now, you think about it, if it was all the way over here, say to -5, when you took the absolute value, you get something bigger than 4. You get something like 5 out. So, like I said, convince yourself of these, but this is the quick way to get rid of the absolute value in a less than or equal to. Absolute value is less than or equal to setting. So we'll replace it with this, and now we'll do our thing like we did previously. Let's speed this one up a little bit. So we'll add 7 to all 3 pieces. This is really 2 inequalities. Add 7 to get rid of the -7 there. 7 plus -4 is +3. 7 plus 4 is 11. 7 and -7 is 0. That'll produce this. Let's divide by 3. Multiply by 1/3 if you like. To get the y by itself, 3 divided by 3 is 1. Less than y, less than 11 divided by 3. That will produce, here it is, 1 is less than y is less than 11/3. So any y, a real number, between 1 and 11/3 satisfies this inequality. If you want it as an interval, then it's all real numbers between 1 and 11/3, excluding the endpoints. That's why we've got the little parentheses there. Along the real number line, we'd go from 1 to 11/3, put the open circles on those, and then shade in everything in between. Absolute value less than. Let's do one absolute value greater than. So this one's fundamentally different. We approach these in a somewhat different way. Same question, basically solve for x. Okay. To get rid of the absolute value, when we've got an inequality of the form absolute value is greater than a number, requires that either that 1 minus x be greater than 1, or that 1 minus x be less than -1. This was the property, this was property 7 of absolute values. So this inequality changes into these 2 inequalities. We'll solve these separately and then union them together. Any x that satisfies either of these satisfies this inequality. All right, so basically solve this for x and solve that for x. In so doing, we'll, let's see, let's take this one and add x to both sides. I add x to both sides, it simplifies down to 1 is less than -1 plus x. I can multiply things. What have we done here? I want to add 1 to both sides. Where's the punchline? It simplifies down to x is less than 2. Yeah, take this, it simplifies down to x is less than 2. Take this, it simplifies down to x is less than 0. We read it as x less than 0. Put all the tedious little steps in there. And we get then that that's satisfied either for x less than 2, or sorry, 2 less than x, or equivalently x greater than 2. These are usually easier to read if you write the x first. So it requires me to move some things around. But we get this first condition satisfied when, it's the first one, x is greater than 2. That's the interval from 2 to infinity. Second one is satisfied when 0 is greater than x. Better yet, when x is less than 0 as an interval, that's the interval from -infinity to 0. So if we get x either in an element of this interval or an element of that interval, then it will satisfy the given inequality. Okay, so here's where we left off. Either x is an element of this interval or x is an element of, here's the other interval. Either or, so if we take the union of those 2 intervals, or if you write it as a union of these 2 sets, that's solution to this inequality. Oh, by the way, on the real number line, here's x greater than 2, and here's x less than 0. Notice the endpoints aren't included because we used open parentheses here. It cascaded down from a strict inequality there. If it was greater than or equal to, we'd shade these in. And what if it was less than? What do you think would happen? If it was absolute value of 1 minus x less than 1, we get the interval from 0 to 2, including or excluding the endpoints as the inequality demands. It'd be like the previous example. So there's illustrations when we have absolute value greater than and absolute value less than. When you have absolute value greater than, you end up with these two pieces as a solution. Okay, one last one says solve this inequality. X minus 1 squared is less than 4. Express the solution set as an interval or union of intervals and show the answer on the real number line like we did before. Oh, use the result, square root of a squared equals the absolute value of a. Okay, they've given us this. Let's take square roots of both sides. Oh, square root function's an increasing function, so that'll preserve the inequality. And when we do so, we get the square root of x minus 1 squared. Well, they gave us the hint. When you take the square root of something squared, you get the absolute value of the something. In fact, that's an alternate way to define the absolute value. So we get the absolute value of x minus 1. On the right-hand side, we get the square root of 4 plus 2. So this question, upon taking square roots, translates into absolute value of x minus 1 is less than 2. Well, that we can deal with. That's like the example we did 2 examples back. Okay, we'll change that into an inequality of the appropriate type. It was absolute value properties 6. So we get x minus 1 less than 2 and greater than negative 2. Or take this, change the sign, put it on the other side. Is what that property told us. We'll go through and add 1 to each of these to get x by itself, and that'll produce negative 1 is less than x is less than 3. So the solution set is all x, a real number, greater than negative 1 and less than 3 is an interval, the interval from negative 1 to 3, or along the real number line, negative 1 to 3, excluding the endpoints, because that's a strict inequality is where that ultimately comes from, and shading in everything in between. One final comment about interval notation. Be very careful that you write the lesser number on the left and the greater number on the right. And if you make the mistake and put the numbers in the wrong order there, you'll certainly catch it when you write it on the number line. But just be careful when you write intervals that you have the numbers in the correct order. The lesser one on the left and the greater one on the right. And that takes care of everything in Appendix A1, and we'll use a good deal of this stuff in Calculus 1, these ideas of inequalities involving absolute values. Big time, the idea that absolute value is how you measure distance, because we're going to do limits and we're going to talk about closeness, and that'll start in Chapter 2. But let me one last time encourage you, check out the video for Appendix A6, where there's a fairly informal discussion of completeness that will get you some level of understanding of what a continuum is. Have a nice day. I will see you in section A6.